Welcome back to our AHIMA CHDA exam preparation course, where we are now stepping into the exciting world of advanced statistics and predictive modeling. In this lesson, you will learn how to move beyond simply looking at historical data and begin using mathematical models to actually forecast future clinical events. Understanding these advanced statistical concepts is incredibly important, because it elevates you from a basic reporter to a highly strategic healthcare advisor. Get ready to discover the mathematical algorithms that allow hospitals to predict patient risks before they even happen. Let us dive into these powerful concepts and prepare your mind for the most advanced portion of the certification exam. To help you master these complex topics early on, I highly recommend obtaining our practice tests or our offline app, which serve as excellent educational resources to reinforce your learning. In the previous section, we talked about descriptive statistics, which summarize what has already happened. But now we must transition to inferential statistics. Inferential statistics allow analysts to take a small sample of patient data and use it to make logical assumptions or inferences about a much larger patient population. Because a hospital cannot afford to test a brand new medication on every single patient in the world, they test it on a small sample group instead. The CHDA exam requires you to know exactly which mathematical tests to use to ensure that small sample accurately represents everyone else. The absolute foundation of inferential statistics is a concept known as hypothesis testing. A hypothesis is simply an educated guess or a proposed explanation for a specific clinical observation, which must then be rigorously tested using math. Whenever you run a statistical test, you always start with a null hypothesis, which essentially states that there is absolutely no difference or no relationship between the things you are studying. Your primary goal as an analyst is usually to gather enough mathematical evidence to confidently reject this boring null hypothesis in favor of an alternative hypothesis. To decide whether to reject that null hypothesis, statisticians rely on a critical metric called the p-value, which stands for probability value. The p-value tells you the exact probability that your clinical results happened by pure random chance rather than because of an actual medical effect. In healthcare research, the standard industry threshold for the p-value is 0.05, or 5%. If your calculated p-value is less than 0.05, it means there is less than a 5% chance your results were an accident, giving you great confidence in your findings. When a result has a p-value lower than 0.05, we officially declare that result to be statistically significant. However, a major trap on the certification exam is failing to realize that statistical significance does not always equal clinical significance. A brand new weight loss drug might mathematically prove that it helps patients lose exactly 1/10 of a single pound, which is statistically significant. Yet, a doctor would tell you that losing 1/10 of a pound is completely meaningless in the real world, meaning it lacks any true clinical significance. Even with strict math, analysts can still make mistakes. Which brings us to the crucial concepts of type 1 and type 2 errors. A type 1 error is essentially a false positive, meaning you accidentally rejected the null hypothesis when you actually should have kept it. In a real hospital setting, A type 1 error is dangerous because it means you believe a new medical treatment works perfectly when, in reality, it does absolutely nothing. The exam expects you to know that lowering your p-value threshold makes a type 1 error much less likely to happen. Conversely, a type 2 error is a false negative, which occurs when you completely fail to reject the null hypothesis, even though a real difference actually exists. Imagine a brilliant new drug genuinely cures a terrible disease,
AHIMA certified coding
but your
specialist
statistical
position.
test accidentally concludes that the drug is completely useless. This tragic mistake means patients miss out on a life-saving treatment simply because the mathematical test was not sensitive enough to detect the benefit. Balancing the risk between making a type 1 error and a type 2 error is a constant challenge when designing clinical trials. When you need to compare the average numerical scores of two totally different groups, the standard tool you will use is called a t-test. For example, if you want to know if male patients have a statistically different average blood pressure than female patients, you run a t-test. The math behind the t-test analyzes both the average score and the internal variation of each group to tell you if the two groups are genuinely distinct. Knowing exactly when to apply a t-test versus other statistical methods is a heavily tested scenario on the CHDA exam. And utilizing our practice tests or the offline app can provide excellent clarity on how these questions are structured. If you need to compare the averages of 3 or more different groups at the same time, the t-test is no longer appropriate, and you must use an analysis of variance, commonly called ANOVA. Imagine a hospital wants to compare the average recovery time of patients using 3 entirely different physical therapy programs. Running multiple separate t-tests would severely increase the risk of mathematical errors. So the ANOVA acts as a single, powerful test that compares all 3 programs simultaneously. You must remember that ANOVA is specifically designed for analyzing continuous numerical data across multiple distinct categories. When your data is categorical rather than continuous, such as a simple yes or no answer, you must use a chi-square test instead of a t-test or ANOVA. A chi-square test looks at the difference between what you mathematically expected to happen and what actually happened in the real world. For example, if you want to see if a patient's gender is statistically linked to whether or not they get a specific infection, the chi-square test is the perfect tool. This test is incredibly common in public health research when analyzing demographic categories and simple disease presence. Moving beyond simple group comparisons, analysts frequently need to understand the relationship between 2 different numerical variables, which requires a correlation analysis. Correlation measures exactly how strongly 2 variables move together, such as discovering that as a patient's age increases, their average medical costs also increase. This represents a positive correlation, whereas a negative correlation means one variable goes up while the exact other goes down. You must always remember the golden rule of statistics, which is that correlation absolutely does not prove causation. The most common way to measure this relationship is using the Pearson correlation coefficient, which is represented by a small letter r. The Pearson coefficient gives you a specific number between -1 and +1, telling you exactly how strong the linear relationship truly is. A score perfectly hitting +1 means the 2 variables move upward together in total lockstep, while a score of 0 means they have absolutely no relationship at all. The exam expects you to know how to read these correlation scores and interpret the strength of the clinical relationship. While correlation tells you that two variables are connected, it cannot predict the future, which is exactly why we use regression analysis. Regression analysis takes the concept of correlation a massive step further by allowing you to use one known variable to mathematically predict an unknown outcome. By taking historical data and drawing a mathematical line of best fit, analysts can forecast exactly what will happen to a patient under different clinical scenarios. This powerful concept forms the very foundation of modern predictive modeling in healthcare. The most basic form of this technique is linear regression, which is used specifically when you are trying to predict a continuous numerical value. For example, a hospital might use linear regression to predict exactly how many thousands of dollars a specific surgical procedure will cost based on the patient's exact age and weight. Because the final answer you are looking for is a continuous number, like money or minutes, linear regression is the correct statistical choice. Understanding when to use linear regression is a critical skill for any healthcare analyst managing hospital finances. When you are trying to predict a binary outcome, which simply means a yes or no result, you must switch to a logistic regression model. Instead of predicting how much a hospital stay will cost, logistic regression predicts the exact percentage chance that a specific event will actually occur. The most common healthcare example is using logistic regression to calculate a patient's exact probability of being readmitted to the hospital within 30 days of discharge. Because the CHDA exam focuses heavily on clinical outcomes, logistic regression is arguably the most important predictive model you will study. By combining these advanced regression techniques, hospitals build complex predictive models that act like a digital crystal ball. A well-designed predictive model can look at a patient's electronic health record today and accurately flag them as being at high risk for developing diabetes 5 years from now. This allows doctors to intervene immediately with preventive care, completely changing the patient's future health trajectory for the better. Predictive modeling represents the highest value a data analyst can possibly bring to a modern healthcare organization. As these predictive models become more advanced, they naturally evolve into the realm of machine learning and artificial intelligence. Machine learning involves writing complex algorithms that literally train themselves on massive amounts of historical patient data without needing constant human programming. The more clinical data the algorithm consumes, the smarter and more accurate its medical predictions eventually become over time. While you do not need to be a software engineer for the exam, you must understand the basic premise of how training data creates these powerful algorithms. A major risk when building these advanced machine learning models is a dangerous technical trap known as overfitting. Overfitting happens when an algorithm learns the historical training data far too well, essentially memorizing the past rather than learning the underlying patterns. When a model is overfitted, it looks absolutely brilliant on paper but fails miserably when you try to use it on brand new, real-world patients. Analysts prevent overfitting by strictly separating their historical data into distinct training sets and testing sets before deploying the final model into the hospital. By mastering all these advanced statistical concepts, you transition from simply reporting historical facts to actively guiding the future strategy of the entire hospital. You now know how to design a rigorous hypothesis test, select the exact right mathematical model, and safely predict future patient outcomes. This incredibly powerful knowledge is exactly what separates basic spreadsheet users from highly respected, certified healthcare data analysts. You have successfully navigated the most mathematically demanding portion of the entire certification blueprint. Congratulations on completing this highly challenging section on advanced statistics and predictive modeling. Because these mathematical concepts are very complex, I highly encourage you to complete the attached practice tests right away. Or open up our offline app to study these equations on the go. Working through these specific statistical problems locks the formulas into your memory and vastly improves your overall exam readiness. The practice tests and offline app are included right here with this lesson to ensure your complete understanding. Keep up this incredible focus. Practice active learning. And I will see you in our final section where we master data visualization and reporting.